This lecture will cover our slides, our week 6A slides here in your files folder so that you can follow along here. Today we're going to be talking about ocean-atmosphere interactions. So last time we had a lecture, we talked about all of the special properties of water, right? And because of its molecular chemistry, life is able to exist on this planet, right? All those different things we talked about, the fact that water as a solid ice actually floats. Water is very resistant to changes in temperature. So all of those things are going to come back into play today when we talk about how does the ocean interact with the atmosphere. And the two together, Earth's oceans and its atmosphere, together create the climate. So we tend to think of oceans and our atmosphere as the separate entities, but they actually form one interdependent system, right, which is called climate. And that means that the two are directly related. So if we cause a change in the atmosphere, we will cause a change in the oceans. If we cause a change in the oceans, that will be reflected in the atmosphere, right? So they're one interdependent system. You can't affect one without the other. So when we define some important vocabulary here, right? Climate is, the definition of climate is what are the weather conditions, the average weather conditions of a place over a long period of time. So based on your position on this planet, right? If you're at the poles, you expect it to be cold. That's the climate. If you're near the equator in the Caribbean, you expect it to be warm. That's the climate, right? It's what you expect. Whereas weather is the short-term variation, right? What's happening on the day-to-day, right? What are the day-to-day conditions of a particular place at a particular time? So it's a really important definition that you have to make sure that you distinguish between these two because they have different meaning, right? You can't use them synonymously. And this picture here helps demonstrate that. So which map above shows weather and which shows or demonstrates climate? So if we look at these two, let's see what we're looking at here. On the left-hand side, we are looking at the African continent, and the colors here indicate the amount of vegetation. So where is it driest, right? So it's drier up here in the tan areas. Over on this side, we have the African continent again, but we have these temperatures, right, dispersed throughout the continent, telling you what the daily high and low will be. So this picture here is of weather, right? This is the short term. It's sunny today. It's raining today. Whereas the long term is reflected in this image, right? It tells, this image is giving you information about the climate, right? What you expect. It doesn't mean that it never rains in the dry regions, right? But that would be weather. Okay, so we know what's in our oceans, right? H2O. Now we have to talk about what's the composition of our atmosphere. So our atmosphere, you can see here from this pie chart, it's mainly nitrogen, about 78% nitrogen. It also contains trace amounts of other gases, greenhouse gases, as well as around 21% oxygen. So this small part here, these greenhouse gases such as argon and carbon dioxide, these are important, and we're going to talk more about these in next week's lecture, okay? Because they're named after something called the greenhouse effect, right? So greenhouse gases, they act like the top glass pane of a greenhouse. They let in solar radiation from the sun, and then they trap it in the atmosphere, right? So it causes this continual warming feedback loop. And the greenhouse effect is also the reason why complex life can exist at the surface, right? Because if you look at Earth's position relative to the sun, the average temperature of the surface should be about 0 degrees. But it's not, right? It's considerably warmer, and that's because of the greenhouse effect, right? These greenhouse gases, this small portion of greenhouse gases, act as the glass ceiling to Earth, trapping heat inside, not letting it escape into space. Okay, so before we get into a little more depth on Earth's climate and some of the mechanisms we can use to predict the direction that wind currents will blow and ocean currents will move, we have to talk about a annual variation in Earth's climate. And you guys may know this as the seasons. So why does Earth have seasons, right, in the first place? So because Earth's axis is tilted, so you can see here, the spin axis is offset by about 23.5 degrees, right? And because of that, you get unequal amounts of sunlight reaching the surface at different times of the year or at different positions in Earth's orbit around the sun. So because this axis is not perpendicular to the plane of the ecliptic, right, or the plane of the solar system, you can think of it, on which all the planets lie, right? The axis is tilted relative to that. And that's probably from when it had its collision with the moon. But because of that tilt, different hemispheres on Earth are tilted more directly towards or away from the sun during Earth's yearly orbit. So this is why we have the seasons here. And this tilt leads to the extremities at polar latitudes. So, for example, the northern hemisphere winter, right, in the area north of the Arctic Circle, it receives no direct solar radiation, right, and experiences up to 6 months of darkness. So, not fun, right? I mean, 6 months of darkness that's a pretty long time. And if this still confuses you, right, it's kind of hard to picture it visually. I have a video here that you can click on and watch, but I won't load it up right now because it makes the videos take forever to upload if I also include other videos. So please have a look at that if this does not make sense to you still. Okay, so let's talk about the main driver of climate on this planet is solar radiation, right? So we know that the sun is the main driver for our climate system. And we also have probably an understanding of, depending where we are on this planet, we can expect it to be hotter or colder. We know that at the poles, we expect there to be ice caps. And at the equator, we expect it to be warm, very humid, tropical, and also very wet. So this has to do with the incoming angle of solar radiation from the sun. So if you look at Earth, right, Earth is a sphere. And because of that, that means that incoming solar radiation will be concentrated over a different area depending on your latitude. Right? So if you look at this picture here, if you're at the equator, right, the solar radiation is concentrated over a smaller area, right? And as you move north or south, the curvature of the Earth means that same amount of incoming solar radiation is spread over a larger area. So if you have more solar radiation in a smaller area, that area is going to be hotter. If you have that same amount of radiation, but you spread it over a bigger area, it's going to be a cooler place. So that's why latitude can reflect the climate or the temperature on this planet is because of the angle of incoming solar radiation on Earth as a sphere. So this slide here is capturing an important vocabulary word that you need to know for your homework assignment and also for your test. And that is the albedo. So when we look at latitude versus solar radiation, right, we can talk about albedo, which is the percentage of that solar radiation that does get reflected back into space. Right, so Earth takes in all of this radiation from the sun, but it doesn't absorb all of it, right? It reflects some of it back into space, and that's what albedo is. And when we look at the latitude of our planet, we can see that there is a connection between the amount of reflected solar radiation on the angle of incidence on a flat sea. So what that means is if you are at the North Pole in the ocean, right? If you look down here, North Pole would be about 90 degrees latitude. So your reflected radiation would only be about 2%, whereas your absorbed radiation would be 98%. So that means that H2O water, right, our ocean water, at the poles, it will absorb 98% of the solar radiation. But if we look over closer to the equator, at 5 degrees latitude, absorbed radiation is only 60%. And the oceans will reflect back 40% of the incoming solar radiation. Okay, so why am I telling you this? Right, so if we think about our planet, we know that we have our ice caps, or we have some ice left, right? We don't have a lot, but we still have some ice caps left. And they reflect solar radiation, right? So ice caps have the strongest solar radiation, and land has the smallest albedo. So land will generally take in more solar radiation, whereas ice will reflect all that solar radiation back into space. So this means that without the ice caps, right, we would go from reflecting almost all solar radiation back into space to absorbing 98% of that solar radiation. So that's called a positive feedback loop. It's when a change in one thing, right, the melting of the ice caps, for example, causes a change in another thing, such as reduced ice mass leads to more absorbed radiation, right, which leads to more warming, and that leads to more melting. So it's called a positive feedback loop. So Earth's climate system is very complex, right? And it's not linear. And so we'll talk more about this in the coming weeks, right? But we'll come back to this picture here when we talk about positive feedback loops. Oops. Okay, so now let's talk about the temperature variations in our atmosphere. Right. So you may not have known this, but our atmosphere is actually heated from below, right? So the incoming solar radiation passes through, it's absorbed by the ground, and then reflected back into the atmosphere. And so it's converted in this process, right? After the solar radiation hits the ground, it's basically converted and it's re-emitted as heat. So because of that, the atmosphere is heated from below. It's heated by that change here. So temperature decreases as you move upwards in the atmosphere, right? You may know that if you've ever flown up in a plane, right? It gets cold when you climb up real high. And below this point, right, below the tropopause, in something called the troposphere, this is where all weather is generated. In the stratosphere, atmospheric temperature will generally increase with increasing altitude. So you can see here, it decreases, it gets colder and colder. And then once you hit the tropopause, right, now it starts to go the opposite direction. And as you climb in elevation, the temperature increases here until you hit the ozone layer. Okay, so before we talk about our air currents, right, and our patterns of atmospheric circulation on this planet, you have to understand some basic concepts in chemistry, right? So let's talk about something called convection. This picture here is of a convection cell, and it's demonstrating something that will apply to Earth on a larger scale in a minute here. But basically, you have a heat source. That could be the sun, or in this picture here, it's the radiator, right? The hot radiator. So the radiator here is warming the air around it, and warm air rises. That's because warm air is less dense, right? So if you need a review of that, it's a really important concept. So get out your notebook right now and write this down. There are core concepts, and if you can learn these core concepts, then you can ace the next exam, right? Because you can use them, you can keep referring back to them to solve different kinds of questions. So the first one of those concepts is that warm air rises and cold air sinks. Warm air is less dense because when it's warmer, the atoms are moving around faster, right? So there is more space between them. Whereas when it's colder, the atoms are not moving as much and they're more packed together. So if you have a lot of stuff concentrated in a small amount of space, you say it's dense. So warm air is less dense, so it will rise. And eventually it can come into contact with something that will cool it down. So in this picture here, that is the cold window. So the cold window cools down that warm air, and so it sinks. Right? So you can see here the cool air is falling, and once it hits that hot radiator again, it gets warmed up. And so it's this self-perpetuating cycle called a convection cell. Right, so convection is where warm air rises and cold air sinks. Right, it's a circular moving loop of air. And this is how air operates on our planet as well. Okay, so before we talk about some of our air currents and we make a map of our planet, we have to also discuss something called atmospheric pressure. Right? So warm air, right, it can also hold more water vapor than cold air because the air molecules are moving more quickly, and so they come into contact with more water vapor. So because of that, warm air is usually moist and cold air is dry. So write that down. That's the second core concept. Warm air is going to usually be moist, and cold air will be dry. So make sure you understand these core concepts. So we'll keep coming back to them when we talk about ocean currents and climate. You can keep using these same principles. Water vapor also influences the density of air. The addition of water vapor decreases the density of air because water vapor has a lower density than dry air. And that makes sense to us because that's why clouds are in the sky, right? So water vapor has a lower density, and if you add something of a lower density to the air, that will decrease the density of that air as a whole. Okay, so then we can also talk about something called atmospheric pressure. Right? So this is what you feel standing at the surface of the earth, right? It depends on the weight of the column of air above you. So that means that pressure increases with increasing distance above sea level. So when you're standing here at the surface, you have Earth's entire atmosphere pressing down on you. But as you take off in a plane, right, and you start to rise up, your ears start to pop, right? You notice the pressure change. And that's because you have less atmosphere sitting on top of you now, right? Now you have some atmosphere below you. So that's what you're feeling when you're climbing in a plane. And this is important. This idea of atmospheric pressure is really important because changes in atmospheric pressure is what causes air movement. Right? So pressure is also a very important concept that we're going to keep coming back to when we are describing Earth's ocean atmosphere system. Okay, so now we can apply the basic idea of the convection cell to Earth's atmosphere and the movement in the atmosphere. So a column of cold, dense air causes high pressure at the surface, which leads to sinking air. Whereas a column of warm, less dense air causes low pressure at the surface, and that will lead to rising air. So here you go. This is your next core concept to write down. Okay, so we've already covered warm air rises, cold air sinks, but now we're going one step further. And we can say that cold sinking air is going to be associated with high pressure, right? And when we look at this picture here, it shows you how far apart each of the molecules are from each other. So warm air, there's more space between the molecules. Cold air, the molecules are packed more closely together. That makes them denser, and that's why they sink. So how can you remember this? If you're standing at the surface here, right, remember pressure is a function of how much atmosphere is above you, right? Is pressing down on you. So if you have cold, dense air coming down and pressing down on you, you can think of that as high pressure, right? Cold sinking air is coming down and pressing down on you. So there's an increase in pressure. Whereas if you're standing at the surface over here, that same air is leaving you, right? So you have less pressure, right? Or it's a low pressure zone, right? So very important you understand these two. Warm rising air is associated with low pressure. Cold sinking air is associated with high pressure. So that's one of your core concepts. Make sure that you know that. And I think I have a study aid as well in your files section with the core concepts that you should know for your exam. Okay, so air movement, right? Air will always move from high pressure regions to low pressure regions. So from high to low. So what is moving air called? Right, so moving air is wind, right? So wind, that means wind blows from high pressure regions to low pressure regions. Okay, so now let's further apply that to our planet as a whole. And before we get into the actual picture of what our air currents look like, let's do an easy example so that we can understand the basics of why air moves where it does on this planet. So let's do a fictional non-spinning Earth, just so we can demonstrate the physics involved. So let's say Earth didn't spin. Right? This is what would occur. More solar radiation reaches the equator than at the poles. So remember back in one of the first slides where we talked about how solar radiation is dependent on latitude, right? And the equator gets the most concentrated solar radiation. So it's warmest at the equator, coldest at the poles. So the equator is warmed. And we just learned that warm air rises, right? So this warm, moist air rises, and we also know that rising warm air means that you create a low pressure at the surface. That's one of our core concepts. So this rising air continues on. It moves upward, or it moves southerly here, until it reaches the colder region, right? Up here in the northern reaches of the northern hemisphere. And so that air cools down, and eventually it will release its moisture as rain, right? So rising air cools, releases moisture. And so because of that, a zone of low pressure and precipitation occurs along the equator, right? So remember, warm rising air has a low pressure system and is going to be associated with humid or wet, rainy climate. Cold sinking air will be associated with a drier climate here. So basically, if Earth didn't spin, you'd have only two convection cells in the atmosphere. You'd have one in the northern hemisphere and you'd have one in the southern hemisphere, driven solely by solar radiation. So at the equator, we have a low pressure system. At the poles, we have a high pressure system. So because of that, we can predict which way the wind will blow, right, on this fictional non-spinning Earth. We saw in the previous slide that wind always blows from high pressure to low. So we said the North Pole has high, the equator has low. So that means if Earth didn't spin, we'd get one wind belt in the northern hemisphere blowing from north to south, and one major wind belt in the southern hemisphere blowing from south to north. Okay, so this ideal picture helps us understand why air moves the way it does, right? From high to low pressure, warm air rises, cold air sinks, and because of that, we have a self-perpetuating convection cell that controls the climate of these regions. But we know that Earth is spinning, right? And so because of that, it's not going to be a perfect linear picture. Because Earth is spinning, things are going to curve as a result of that spinning. Air currents are going to curve from their original path. And that's called the Coriolis Effect. So make sure you understand the Coriolis Effect, right? The next exam talks a lot about this, because everything in the oceans, whether it's the wind or ocean currents, all those types of things are controlled by the Coriolis effect, the fact that Earth is spinning. And it's a result of the rotation of our planet towards the east. So what happens is, because Earth is spinning, moving objects such as air are going to follow curved paths, not straight paths. So in the last picture we saw, air currents moved straight up and down, right? But you can see here that's not the case. They actually curve. Air currents curve because the Earth is spinning, and that's called the Coriolis effect. The Coriolis effect is that deflection or curvature of that moving particle, that air current, due to a spinning Earth. In the northern hemisphere, this is very important, because in the northern hemisphere and the southern hemisphere, the deflection or the curve is in the opposite direction. So in the northern hemisphere, an object will follow a path to the right of its intended direction. So you can see that demonstrated in this diagram here. Coriolis force steers motion to the right. However, in the southern hemisphere, an object will follow a path to the left of its intended direction. So you can see that reflected down here. So in the northern hemisphere, it's to the right or clockwise. In the southern hemisphere, it's to the left or counterclockwise. And you may have heard that analogy before of Maybe you've heard toilets in the southern hemisphere, though when you flush the toilet, the water spins the opposite way, right? And that analogy comes from the Coriolis effect, right? The fact that things are deflected in different directions based on the hemisphere that they encompass. And this effect, this curvature, this deflection gets more and more pronounced or more obvious on objects like air currents that travel long distances, right? So the longer the distance over which the air current has to travel, the more dramatic the curvature will be over that distance. Okay, so we know that Earth is spinning and that this is causing a deflection of moving objects. So now let's look at a little bit of the physics of why. Why does a spinning Earth cause this deflection? Well, it comes from the difference in the speed of Earth's rotation at different latitudes. Right? That's what causes the Coriolis effect. Because spinning velocity, how fast Earth is spinning, is greatest at the equator, and it's zero right at the poles. Right? So you can see that demonstrated here in this diagram. At the middle of our planet, at the equator, the rotation speed is 1,650 kilometers per hour. And as you increase your latitude, north or south, right, that speed gets slower and slower until it hits the pole where that speed is zero. So if you think about this, right, how do we measure speed? What is speed? Well, if you're driving on the freeway, you're going like what? 75 miles per hour, right? That's your speed. So miles per hour, distance over time. So how much distance did you cover in what amount of time? We know that no matter where you are on Earth, right, one rotation, right, one day will be 24 hours. Right? Doesn't matter where you are. One day is going to be 24 hours. But we know that Earth is a sphere, and that means that it's widest at the equator and it's narrowest at the poles, right, where it comes to a point here. So because of that, that means that this part of the planet, the middle part, has a much bigger radius, right, than the poles. So that means in 24 hours, more distance is covered, right, at the wider parts of our planet than at the narrower parts. And speed is distance over time, right? So because of that, you're moving at a faster rotation speed at the equator than you are at the poles. So this is the Coriolis effect. An air current tries to take off from the equator and move northward, but it moves from a region of fast velocity into a region of slow velocity. So it can't continue on its path, and it ends up curving and getting deflected because of this difference, this change in spinning speed causes that deflection here. So that's what's going on. That's the physics of what's going on. But there's an interesting video that let's take a look at here that demonstrates this at a playground. So you can see in the next slide I have, this assignment. Don't do it though. Right? Don't go to a playground, stay home. But there's a fun example that they do here. Let's have a look.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
All right, here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough, like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah, I don't know.
Right, what's going to happen, dude?
It's going to veer off to the left.
So the ball is going to swerve off to the left.
Yep.
And you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more.
He's
Spencer.
not arrogant.
Just quietly
He's
confident.
not catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
Right, in your own time, throw the ball.
I got this. Oh!
Whoa.
I told you it was gonna happen.
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, I did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea.
It's called the Coriolis Effect. And it's very simple. It's objects in motion it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight. It's still going straight, but the table is moving below you. And all of a sudden, look who's in front of that straight moving ball. And it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to. And that, ladies and gentlemen, is the Coriolis Effect.
Okay, so the Coriolis effect is why air currents and ocean currents will deflect on this planet. So here we can see a map of our convection cells as well as our major wind belts. So they're broken up into these latitudinal sections, right? So because things can't make this straight intended path, they deflect here. So on the right, this is the non-spinning Earth, and then on the left here is our spinning Earth. So we can see at the equator we have a low pressure zone. At 30 degrees north and 30 degrees south, we have a high pressure zone. So that means we have cold sinking air. Low pressure zones are associated with warm rising air. And we know that warm air contains more water vapor, so it's going to be more rainy and more wet. Whereas cold sinking air, remember, it's drier. So it's going to be associated with a clear and sunny climate here. So you have these different latitudinal bands and wind belts. Remember, wind blows from high to low pressure. Right? So that means that we can draw this map with very little information. We have a high pressure zone here at 30 degrees and a low pressure zone here at 0 degrees. That means wind will move from high to low. It will blow from north to south, but it will curve to the right of its intended path because of the Coriolis effect. Whereas from 30 degrees south, we have a high pressure zone here and a low pressure zone there. That means wind will blow from south to north. But since we're in the southern hemisphere, remember, the Coriolis effect is going to deflect things the opposite way. So things are actually deflected to the left in the southern hemisphere of their intended direction of travel, right? So from the base of the arrow. Okay, so we have that picture of a spinning Earth, but there's a couple things that also complicate the picture, right? So it's not a mirror image. The last slide's not a mirror image of a perfect Earth because Earth's axis is tilted, which produces the seasons. And also, the lower heat capacity of continental rock compared to seawater makes the air over continents colder in winter and warmer in the summer than the air over adjacent oceans. And the continents are also important, right? So the uneven distribution of land and ocean over Earth's surface, right? This distribution will also control and influence small-scale weather patterns. So you can see that demonstrated here. You have South America, low pressure zone, Africa, low pressure zone, Australia, low pressure zone. And between each, you have this high pressure zone that sits here, right? So this high pressure zone is broken up by the continents, right? Because they will establish this low pressure zone here. Okay, so also have a look at this video too. That will also demonstrate some of these non-ideal, non-symmetric weather patterns here. Okay, so now let's look at a U.S. weather map showing the atmospheric pressures and associated winds. Okay, so over here on the West Coast, we have a high pressure zone. Over here on the East Coast, centered in the Southeast, we have a low pressure zone. So if you look back to your notes, right, that you've been taking, high pressure is associated with what type of weather? Right, remember, high pressure is cold, sinking air, which is dry. Low pressure zones are going to be warm, rising air, which leads to a moist, humid climate. So that explains why it's very swampy down here, right? And whereas it's relatively dry over on the West Coast, right? And this is the average, right? This is the climate. We know that individual areas may receive more or less rainfall than others, depending on local topographic features like mountain ranges and things like that. But generally, we have these two pressure zones that sit here. So looking at this picture, which direction would wind blow, or we would expect wind to blow over North America? So we know that air will move from high pressure zones to low pressure zones. So that means that wind currents blow from the west to the east here. And you may have noticed in the plane, if you've ever flown out to the East Coast, right, there's something called the jet stream. And it's a quicker flight if you're going one way as opposed to another, right? Because you're going against the jet stream. You're going against that major wind pattern here. Okay, so now let's apply this to coastal regions, right? There's two important vocab words for you to know. And we can refer back to what we learned last week in seawater chemistry. Remember that water, H2O, has a very high heat capacity, which meant that water can withstand temperature changes without warming up its baseline temperature, right? Whereas land, on the other hand, has a low heat capacity, meaning on a hot day, the land will absorb all of that heat, right? So this difference creates the sea breeze and the land breeze. A sea breeze occurs during the day when air is warmed by the land. Warm air then rises because it's less dense, and it's replaced by the cool air from the ocean, right? So during the day, the land warms faster than the ocean because ocean is made of H2O, and we know that H2O has a high heat capacity. It resists temperature changes. So during the day, you have a warm zone here and a cold zone here. And we know that wind will blow from high to low pressure. And if we look back at our core concepts, we know that cold sinking air is associated with high pressure and warm rising air is associated with low pressure. So that means that during the day, you will get a breeze that comes from the ocean towards land. That's called a sea breeze, right? It's a daytime breeze. But at night, the opposite is true, right? So during the night, the land cools down faster than the ocean. Remember, the ocean is resistant to temperature changes. So that means that you'll have a cold sinking air zone on land, or a high pressure zone on land, and a warm rising air, low pressure zone out in the ocean. So wind, remember, blows from high to low. So at night, you get a breeze going the opposite way. You get a land breeze, which is a breeze that blows from land to the ocean. And this is why people love to live along the coast. It's not just because it's very beautiful. Coasts are also very temperate, right? The difference between the daily highs and lows is very narrow, as opposed to if you lived further east, right? Because the ocean is H2O, and it has this this very interesting effect in that it basically makes a region more temperate, right? Because of the presence of water, you have a high heat capacity that resists temperature changes and keeps the region at a relatively constant temperature. Okay, so next lecture, we're going to be talking about ocean currents. And so we're going to come back to this, but I'm going to give you an introduction today. So let's talk about tropical cyclones. What is a cyclone? So the definition is that it's a huge rotating mass of low pressure, characterized by strong winds and torrential rain. So they're basically the largest storm systems that occur on Earth. And in North and South America, we call them hurricanes. In the Western North Pacific, they're called typhoons. In the Indian Ocean, they're called cyclones. But it's the same thing, right? These huge rotating masses of low pressure, right? With these really strong winds that can be really damaging to infrastructure. So when we come back to lecture next time, we're going to talk about why is it that hurricanes always seem to hit the same spots, right? Why is it they always seem to hit the same spots? It's not a coincidence. It has to do with the ocean currents. Okay, so what are the conditions needed for a hurricane? So the source of energy, right, is from water vapor that's evaporated from the ocean surface. And remember, low pressures, wind will always blow from high to low pressure. So this low pressure zone causes the wind to begin to spiral inward, right? Because wind blows from high to low. So it starts to spiral inward towards the center of that low. But you also need to have the sea surface temperature be warm enough to trigger a cyclone. So this is about 25 degrees Celsius. That's the minimum temperature that you'd need, because warm, moist air is what fuels the storm, right, through condensation. So when we are describing hurricanes and describing the intensity, we use the Saffir-Simpson Hurricane Intensity Scale. So similar to how we rated volcanoes and earthquakes, right? We also have a scale for hurricanes, right? So this is indicated by the colors here. 5 is the largest hurricane you can get, and blue is the lowest, right? We call it a tropical depression or a tropical storm. And once it becomes a hurricane, we assign the number 1 through 5. So you can see here's a map of where hurricanes tend to occur, right? So we know we have a hotspot region over here in the southeast of North America down by Florida, right? But they also have a lot of threat over here too in the Western Pacific. A lot of hurricanes occur in this region as well. And this picture here breaks down how the categories work. Right, so if it's a level 1, you're looking at winds of 119 to 153 kilometers per hour. If it's a 4, right? It's 209 to 251 kilometers per hour. And they even include a little picture of the damage, right? So similar to how we use the scale in earthquakes based on, infrastructure damage, we also use that for hurricanes. So you can see, a 1, you'd have dangerous winds, and maybe you'd get some damage to, poorly constructed homes, tree branches, power lines. And then it just goes up, right? So if you get to a 4, right, roofs and walls will collapse. Most trees and power lines are down. You're getting flooding, and the area is uninhabitable for weeks or months, right? So it's really important that our climactic organizations like NOAA, right? Remember the National Oceanic Atmospheric Association, right? They're like NASA for climate and oceanography. And so it's really important. Their job is to track these tropical storms in the Pacific, Atlantic, Indian Oceans and predict whether they will become and how intensely they could become what type of hurricane, and making sure that the people are informed and evacuated if need be. Okay, so I want you to click on this figure on your own time so you can sort of understand the track that a hurricane will move. But we're also going to come back to this in your next lecture. We talk about ocean currents and how we know and how we can predict the direction that storms will move over the ocean.